for it. I didn't even think about it as I was talking about it, but you're right. It's absolutely phenomenal to think that that much salt could have that big of an impact on the freezing point. So it's, just a little housekeeping here. Go back when we were talking about the factors influencing the freezing point. 1 gram of the molecular weight of salt, whatever salt you're using. As you know, potassium chloride might have a different molecular weight than sodium chloride, and so on. What the point is that for every gram, and this is per liter of H2O, it leads to a depression of the freezing point of 3.72 degrees, not 37.2. Big difference, okay? And if you're looking in Fahrenheit, that would be 7.04 degrees Fahrenheit, okay? If only 1 gram of salt could lower freezing point that much, right? Think what an impact that would make on the food industry. All right, and then the other thing that I kind of wanted to bring up, I'm sorry. Yes, sir.
I was looking at the textbook. I'm not, because the wording's a little weird. I think it's a mole of salt. So like for sodium chloride, it's 58 grams. They say like gram molecular weight as 1 chunk, rather, because it's a weird, the way they phrase it is like a little strange.
You mean 1 mole total?
Yeah, so each mole of salt,
which would be
58 grams, lowers it 3.72.
Well, but what kind of salt are you talking about?
That's sodium chloride.
Yeah, so it's different for each salt. So this is kind of just but you're saying that it's 1 gram of not the molecular weight, but the mole?
So it's like, the way, instead of saying mole, they write gram molecular weight. So
yeah. Okay, yeah.
Okay.
Thank you. So yeah, so for every single, so in other words, a gram of that molecular weight of salt, right, which would be a mole, is what you're saying.
Right, so like 58 grams.
Yes,
okay.
Well, for sodium chloride,
Yeah.
but for each salt it would be different. So this is a generic formula. Okay, thank you. Thank you for that. I'm never going to make you figure this out, you guys.
Okay.
This is as deep as we get in here, okay? Honestly. If you go on in food science, you'll have people who have much bigger brains than me explaining this stuff to you, okay? I'm basically a nutritionist, all right? When we get to the real nutrition part of this course is where it's going to get fun, like carbohydrates. All right, so someone else had a comment they wanted to make.
It was the same one.
Oh, thank you so much. Oh my gosh, you guys. I probably could ask several of you to teach this particular part of the course, and it would be much clearer. So thank you for putting up with me. I appreciate that. And then someone else brought up, they had just had physics, and they found it very confusing when we talked about the heat of fusion. And I hope that you've read your textbook by now and you've seen that figure. But the heat of fusion I described to you as going from a liquid to a solid. And basically, the delta H was negative 80 calories, right? Okay? So, in other words, it was a negative. Well, this is called, what's it called when liquid goes to a solid?
Fusing.
It's called melting. Right? I mean, look at those some cheesy Pete, guys. I'm not even listening to myself. It's called freezing. Okay? When liquid goes to a solid, it's called freezing, and it requires 80 calories. Right? All right. Well, you know what? This same definition, and that's what some people call the heat of solidification, but it's still the heat of fusion. Going the other direction is melting. And it's got a positive. It's got a positive delta H, okay? So if you look this up and look in your text or go online and do some further research, you'll see that the heat of fusion is considered both directions. You just have to know one is a negative heat and one is a positive heat. In other words, one requires heat, one gives off heat. Does that clear that up a little bit? But in this course, the way it was presented to you, the way the book presented it to you, it was doing the freezing, okay, liquid to a solid. Okay? Does that help with that, or have I just confused you even more? All right, and then to continue to finish our lectures on water, we're going to look more at, we looked at influences affecting the boiling point and the freezing point. Now we're looking at bound water. And bound water is exactly what it sounds like. It is water bound to food particles, most importantly proteins usually. And it's tightly bound, and therefore, so this water, this is tightly bound water to food components or particles. And this being bound leads to inactive water. So we've got water that is not, water does not follow the flow pattern that we expect. And as you can imagine, this greatly changes the functionality of that food. So this water that's bound to these tissue membranes, these food particles, you can put tissue membranes, think protein. These things become so tightly bound that they're not going to exhibit the flow properties that we expect water to exhibit. So it contributes significantly to the textural compound characteristics of the food. For example, so say it actually alters food characteristics. For example, you've got dried gelatin, the powder. When you add water to it, that water becomes bound to that gelatin. Have you ever been able, you know what it's called when gelatin becomes bound to water? What is it called? What do you eat?
Jello.
Jello. Okay? And have you ever tried to unbind the water from Jello? Kind of hard to take it back. It is bound. So the flow properties have been changed. And clearly, we would not have Jello without bound water. Here's the cool thing. It's another great example of how war and the space program has impacted our food industry. If it weren't for wars, unfortunately, we would not have many of the foods that we have now. Jello is another example of a food that was created for astronauts. Can you see how easy it would be to package all these powders on the Apollo or space module or whatever, and adding water to it in what?
I was just imagining making Jello in space.
I know. I know. Oh, well, clearly they have different things. They have all kinds of dry products they add water to in space. So clearly they have a controlled, okay. It's sort of like, with that astronaut being asked, how do you urinate in space? I mean,
Still not sure.
Well, I am, because I've asked that question, and I have a friend who actually works for NASA who has done some of the food development. She was a professor at University of California, Davis, and she now works for NASA. Anyway, the point is that Jello is another example of food, of how the space industry and war, quite frankly, have impacted our. All right, so moving on. Moving on now to water activity. Where's that yellow thing? I like that yellow thing better. It's more my size. Water activity is a concept that especially people who work like in the food industry have to be aware of, because it's what's going to help control microbial activity. Because you remember water, oxygen, oxidation, microbes, they need oxygen too. Well, some don't clearly, but aerobic microbes do. So water activity in food is extremely important. And so that has to be measured, and in some cases, quite frankly, altered. So the water activity of food, and it's always written like this, little a with a sub-font W. And it equals the vapor pressure. Can I just abbreviate pressure as press? Is that okay? Okay, of the water in food, in the particular food that you're looking at, do I need to write particular food? You know, we're doing this individual for each food, so the food, over the vapor pressure of water. Now, food, the AW for food, is always going to be what? You think it's going to be 1 or less than? It's always going to be less than 1. It's never going to be equal. In other words, the vapor pressure of water in food is never going to equal the vapor pressure of pure water. Because if it did, it'd be pure water. You know, there's stuff in the food, right, okay, that makes the vapor pressure going to be less than 1. So, we look at the resorption and the desorption of food. Clearly, resorption is the uptake of water. Desorption is the loss of water. So, think of an example of a food that's something that's resorbing. The dehydrated products, correct? Dehydrated products would be resorbing. How about meat? Do you ever marinate your meat?
Yes.
That's a form of resorption. And then desorption. Yes, sir?
When your meat is marinated and like sucking up the juices, absorbing it, wouldn't dehydrated be going the other direction?
Well, you're thinking of a pure case, you mean like it's losing water, actually, but it's soaking in things that are still probably, thinking of the tonicity. No, it's soaking up water.
Well, it's like, are you putting dehydrated stuff like lentils in soup, or are you talking about like making beef jerky? Are you taking the
Oh,
water?
no, I'm not talking about, yeah, I hear what you're saying.
You know what I mean? Like a dehydrated product.
Yes.
You're taking water.
Yeah. Okay, resorption, okay, means that you are taking up water. Okay, the food itself is taking up water. Okay, thank you. And desorption is the food losing water. Is that clear to everybody? I know sometimes it can be confusing, especially when we talk about bones and resorption. Okay, so this resorption and desorption, this can create a record. You can actually measure this, and that measurement is called an isotherm. You'll not be doing this in class. I'm not going to be making you do any calculations and the math that goes with this, but I'm going to tell you something. Why do we care about this? Because sometimes altering the water activity of a food is desirable. For example, think if you're trying to create a food that has less spoilage. And your example of beef jerky is a good one. I think I wrote down that I really like the table. There's a table in your book I think you should look at. And it has the beef jerky, table 2.6 in your text. Has a very good example, not only of the decreasing amounts of water in the food and water activity, but also then how temperature impacts it. For example, this is just an example here. A food with high water, with lots of water in it, okay, then it's got a good chance of high microbial growth. Microbial growth, okay? Especially temperature. With high temperature impacts it. So the higher the temperature, more growth. Does that make sense to you guys? Heat and oxygen, for many microbes, it increases their growth. So you've got a food that's got a high water activity, and it's going to maybe not necessarily be in the type of temperatures. Let's say it's going to be 20 degrees. Let's say it's not going to be frozen. Even sometimes a refrigerator temperature, we can have high microbial growth, which is why food doesn't last forever in a refrigerator, even though it's cold, right? So it might be desirable to lower the temperature. Hence, dehydrated soups. These things last longer. I'm going over to Dehradun, India, okay, where I work frequently. I pack in my suitcase dehydrated packages of soup and macaroni and cheese, or the little noodle things. I take dehydrated things because I know they're going to last forever, and all I have to do is add water or hot water, right? So, and think of the other types of work that people do where this is going to be desirable. So, in general, food with less than, not equal to, 12% moisture have got very little microbial growth. And that's the general rule of thumb in food science that most of these food manufacturers go by if they're trying to present something that they know needs to last for a long time. So these food scientists use isotherms quite a bit to determine which way they want their food. Yes?
Is that 12% moisture by volume or 12% by
I don't know. It's a great question. I'm assuming by weight, quite frankly, but that would be because it's dry. That's what I'm expecting. All right. I love you. I do. I think you're fabulous. All right. So, so again, look at table 2.6. And you'll see there that they compare the water activity of distilled water to dry soup mix to beef jerky to sausage. Which one of those do you think has the highest water activity? I hope you say sausage. Well, water, excuse me, clearly does. But of those other ones, then sausage, and then beef jerky, and then the dried soup mix. But what this particular chart shows you is the effect of temperature on each one of those things. And as temperature increases, you find that the water activity of the dry soup mix almost triples. And the beef jerky, it stays about the same, and the sausage, it stays about the same. Isn't that interesting? The temperature has a bigger impact on the dry soup mix than the beef jerky and the sausage. Why do you think that is? As temperature increases, is there more or less moisture in the air? More. So the air can hold more moisture. So it's going to have the largest relative impact on the thing that has the least amount of water. Isn't that interesting? Yes. Oh, I thought I saw a hand. All right. So, and then you also want to look at, if you're in food preparation, the hardness of the water is going to have an impact. Hardness of the water. What does hard water mean? If my water's hard, then what does that mean?
It's got a lot of minerals.
It's got minerals in it, exactly right. Calcium, magnesium. I always tell the athletes I work with, quit drinking bottled water, drink your tap water. Because that's got all the minerals that you think you need, the magnesium, the calcium, the sodium, it's got it. Drink your tap water. In this country, our tap water is some of the safest, well, the places I go, they would die to have, literally, I mean die to have the access to just turning on a tap and having fresh water. Wow. And yet in this country, we go out and buy plastic things. I'm just as guilty. I've got a Fiji bottle in my office right now. I love it. It has a little silicone in it, the natural silicone from the falls, and it feels so soft and smooth. Michael Jordan likes it too, so you know. Anyway, here's the thing. While I'm standing here talking to you about bottled water and the bottled, my son-in-law who played football for Cal, was an offensive lineman. He got his degree in civil engineering, specializing in environmental engineering, and he has a master's now in it. He works in biomimicry, meaning he goes to different, like he was in the Amazon, and for 6 days, they watch how nature's beetles deal with excessive rain, and then they reverse engineer. This is called biomimicry. And it's growing and growing, and he is constantly talking about water bottles and making it. He makes me feel terribly guilty, and plastic and any petroleum-based product. And I understand, this storm in Texas right now. By the way, my family's fine. Thank you for asking. They are stranded in Houston. The roads are still flooded. They haven't gone anywhere for 4 days, which I think could cause more casualties in my family than anything else, being in the same house together for that long. But they aren't moving, and luckily, being Texans, I mean, my sister has 3 freezers full of food. I'm not kidding. That's the way they are. One's just full of beef. All right, they split a cow each year, but anyway, so they're fine. But my son-in-law, your Cal alumni, he is saying these once a century events are going to start becoming once a year, and they kind of have been, and it's because of climate change. And so, looking at the plastic and all this kind of stuff, you know, I don't know that we need that. I think I'm being lazy that I'm doing that, right? But let me give you another perspective. In other parts of the world where they don't have clean supplies of water, bottled water is saving lives every single day. So, what do you think? What do you think? It's destroying the planet, but in an acute setting, it might be saving lives. The number one cause of death in infants in developing nations is diarrhea in the first 6 months of life. And it's because of the mothers who have AIDS, and weak breast milk can pass the AIDS virus. And so many of these mothers think, and Nestle, the big devil, they are the ones who put out formula and say, use the formula with your babies, and that way you don't pass AIDS. Well, guess what? UC Davis did a study, Kay Dewey, she's the big lactation specialist in the world, and they found that more infants died who got formula than got the breast milk from their mothers with AIDS. Why do you think that is, considering the discussion we're having right now?
The water.
Dirty water. And so these infants got infections, diarrhea, and when an infant gets diarrhea, it's life-threatening. And you've got to remember, these populations have no clean water. They don't have toilets and toilet paper. They don't have diapers. So think about it. An infant has diarrhea. Who deals with that? The mother. Does she have soap? Does she have clean water to clean her hands? She's also dealing with 5 other children. Do you think any of them might get sick? What about her? But the infant, then they try to clean the infant. The infant now not only has diarrhea, it's becoming dehydrated, now you're reinfecting it because you're touching it. And you touched the diarrhea as well. Diarrhea is deadly in these settings. So, bottled water or not? First of all, encourage the mother with AIDS to nurse anyway, period. But what about bottled water across the world? I mean, even though it's killing the planet, what do you think? Yeah.
Do you think it varies? Like, for example, like Flint, Michigan?
Flint, Michigan?
Like, they had a water system, but because
Right.
of regulation.
Yeah.
So do you think it just varies on the government?
Well, he brings up Flint, Michigan here in this country. Flint, Michigan had the water problem that you guys heard about in the news. Their water, I think had too much, was it lead or mercury? Lead. And that's supposed to be against the law. There's all these standards that are set up that are supposed to be controlled by the EPA and all these other groups, and clearly that failed. So is the answer from an acute setting? Let's look at an acute setting. The answer might be get them some bottled water, but is that the chronic solution?
No.
What do you think the chronic solution should be, or long term?
Clearly better infrastructure.
Better infrastructure. In other words, let's go in and replace the pipes. We're one of the richest countries in the world. Shouldn't we be doing that? Shouldn't we be spending money on that? Write your letters, people. Write your letters to your congressman. But what about other nations? What about these nations like India that doesn't like to consider itself a developing nation? We are already developed, and I am telling you that India is a third world country. Tell me, what do you think about nations like that? I mean, do we have the political power to go in and say you should do this, or we aren't going to be a trading partner with you unless you quit using bottled water? Because you're destroying the planet. There is a plastic thing the size of Texas floating around the ocean right now. What do you guys think about this? I want to know, where do you stand? I know you may not stand anywhere right now, but have you thought about it? Yeah.
I mean, I consider it a short-term solution for acute problems to use bottled water or tap water. But in the long term, it's like political background to go into place in order to get infrastructure and such.
Do you think that there is any obligation of a country, I'm not saying what country, who has a lot, do you think there's a certain responsibility to share not only their technology, but their talents, their time, their treasure, et cetera? Do you feel like this country has a responsibility to help other nations improve their infrastructure by providing the talent and the, I mean, what do you think about that? I'm curious, because we gotta take care of our own as well, yeah.
I think it's hard to judge other countries based on the perspective of this country because we're lucky enough to have tap water that, for example, is clean and we can drink it. Yes, maybe we have a responsibility not to use plastic, but by no means is the U.S. Allowed to potentially, or just us, judge other people for using it because they don't have the same opportunities.
I'm not asking you to judge, actually, quite frankly. I'm asking you, and I hope that's not what you thought I was asking you to do, because I'm certainly not respecting. And as from an international nutrition, we definitely have the idea that we go in and we offer solutions and they decide, if they ask us to. But I guess what I'm asking you is, do we have any kind of responsibility, just as a nation who has a lot? I'm just curious what you feel, yeah.
No, because I think that it's maybe forward to assume that a lot of Western luxuries are going to be easily transferable to, say, like Africa or say, like a different culture, completely different culture. And if you look at humanitarian case, when they, level medicines, there's a lot of medical healers that just use the land, use nature, use plants for heal. They don't know how to apply needles, they don't know how to apply, so they can really go to like the healing side. You'll find like packages of needles because they don't. So the fact this is like.
So we shouldn't share our AIDS medication with all that?
No, of course we should, but I'm saying is like.
That's needle, but anyway, I hear you.
You know, I think applying a Western view of how to develop a country is a very poor way of handling humanitarian aid or, form of development for a country because not all countries develop the same.
You need to take my international nutrition, my cultural nutrition class in the spring. This is what we talk about a lot, and this is what clearly my field is, but I appreciate what you're saying, and it's been a long time coming for this understanding to develop. But I still, as a group of scientists, if we have this amount of knowledge, do we not share penicillin with the world? Do we not share vaccinations for polio with the world? Do we just let people die of malaria because they are not the same culture? And you see what I'm getting at? Can you imagine being in the group where you know the solutions to some of these problems, and yet do you share? You see what I'm getting at? It's a real conundrum. It's not quite. It's sort of like saying, we're done. Yes, ma'am.
So I think another way of looking at it is that in a country that has a lot of resources, you can use that privilege to innovate. And so I'd like to start up with something like, I think it's solar powered in water bottles to clean the water. And so that's not just like giving people bottled water or saying you shouldn't use it, but it's another solution.
Dear, she said there is a group that it's a wonderful group. They're using solar power to purify the water, and they're teaching different individuals how to do. In Mexico, we had a group that had terrible pellagra, and we taught them how to ferment their own corn so it reduced the thiamine blockers. In Nepal, they asked us though to come in, and we actually created a system for the women to not be nightblind anymore. I think I talked about that already. So a lot of this is being asked to do it, but some of it is there responsibility for those of us who have solutions to say something? Yeah.
I think there's a big distinction too though between providing resources to countries who need it and then trying to delegate how they develop their own countries, because the fact is like we benefited from like the first industrial revolution so much, and like we did so many things that we like abhorrent in our eyes now in terms of like what we did to the environment to get to the point where we're at like economically and socially. So to like go like to take our like advantages and try and like regulate how like third world countries are trying to like advance their like stuff industrially or whatever is like so, I don't know, it's so hypocritical of us to like go and be like, hey, you need to like regulate like your coal like outputs and stuff, when it's like you look at how we got to where we are and it's just like through like blatant deregulation and stuff. So
Okay, well, let me thank you for that. This is a very I think very well thought out argument as well. Let me play the devil's advocate just a little bit, because like Brazil, for example, says, quit telling us to cut down our rainforest. Do you know that what they cut the rainforest down for?
Palm oil?
To grow beef. Do you know where they sell the beef?
Here.
Here. You're eating the beef that is from the rainforest that's been destroyed. So again, there's a real conundrum, right? How do you know that the beef you get from McDonald's, that hamburger you get or whatever you get, how do you know that didn't come from Brazil? And they cut down the rainforest and they say, what the right do you have to tell us what to cut down or not? You eliminated, look at all the deciduous forests you eliminated. Look at the redwoods. Look at what you have done. How dare you say that to us? All right, so that is one side of the argument, which is very, I think, but let me play the devil's advocate. We are a global economy now. And what one country does, because of the huge, back when the United States was doing this, population was maybe 1/10 of the size that it is now in the world. And so now with India and China, their populations combined are more than all other nations in the world together. All other nations could disappear, but China and India, and there would still be more people on the planet than had been lost. Did you know that is, and it's continuing to increase. They're the two fastest, India is the fastest exploding population in the world. So the point is, what these two countries do impacts us. It impacts our environment. It impacts our water. It impacts our fishing. Okay, so from that side of the argument, do we now have a right? I mean, it's real hard, isn't it? What do you think?
Well, I wanted to reiterate what one of my classmates said over there is that there's a lot of ability for nations that now are considered first world countries or are better off economically to innovate and to create like composting toilets to get rid of sewage problems and other things.
But do we share that information, or is that considered invasive?
It's definitely something that should be shared and should be passed on. It's not something that necessarily you need to say this needs to be implemented, but sharing ideas and also resources to implement those in other countries is something that's important. Because I can't remember which country, like in the Netherlands, or I know that a lot of, like Swedish countries and other places like that have been providing resources and money and saying that we'll help developing countries go through this process.
They don't like being called developing countries, by the way. I mean, they don't like being called third world. It's difficult, and I can understand that sounds like we're being kind of big parent, little child. So, but I appreciate your comments. Yes.
Just on what we were saying about Brazil criticizing us, criticizing us. I think it's just hard from like an ethical standpoint to say that. Well, the only people.
I hope that these discussions mean something to you guys, and you actually listen to your colleagues who are bold enough to share their opinions to the class. I think it's respectful to be quiet and listen to what they have to say. I appreciate their comments. Yeah.
Just like from an ethical standpoint, if we're to say that the only people that can speak out or criticize other people are people who have done nothing wrong, no one will be able to say anything. But also it comes with a sense of shared responsibility. If we are going to say that people who are doing the wrong thing are able to criticize others.
What do you think about that word, shared responsibility? Kind of like, in a way, it's sort of like admitting that, yeah, in the past we kind of made some wrong decisions, but we've learned from those wrong decisions. Let us share that information with you. I don't know. You're right, though. It's a real conundrum, isn't it? And it requires a bit of finesse, which we may not have right now in our political scene. Finesse is not a word I would necessarily use. Last comment. Yes, ma'am.
There's also, like, speaking of, like, the growing populations in China and India, like, the U.S., like, despite being, like, a small country relative to, like, the world population, consumes so many resources, so they watch it, and then, like, China and India watch it do the same thing, we're like, oh, no, you guys should stop, so we can, like, keep on, like, consuming all these resources. So, like, how hypocritical is it that, like, Americans eat, like, so much meat, and, like, but they're saying, like, oh, but, like, climate change is worsening because Chinese people are
Yes. So she's making the comment that there is a real ethical paradox in that we're encouraging the rest of the world to slow down their consumption or to help improve the global warming, when actually, do you know that the United States has been on a negative population growth now for decades because people are only having one child or two children or deciding not to have children. So negative population growth, I'm not saying that's good or bad, it just is what it is. Look it up, okay? So that means that within 10 years, hold on to your seats, the 90 plus age group is going to be the largest age group, and it's going to be larger than all the other age groups combined in this country. Now, the good news is that means we're living longer. The bad news is they're all in Social Security, and who's supposed to provide all that money? You guys better work hard. I want you to support me. This was done, a research by a professor out of the University of California, Riverside. Look it up. It's an amazing study. Anyway, the point is that we have got about 3 to 5% of the world's population, and we use about 80% of the goods.
We create the most waste too.
And we create the most waste. So it's hard to stand on the leg, isn't it? All right, well, thank you so much for having this discussion with me. I like to have these, I think it's important that as students, at some point, we get out of the book for a minute and just talk about the implications of what we're doing. Food science can have a huge impact on the global economy and the global waste. Think of all the waste that your food products, look in your pantry and see how many boxes are in there. How many things do you have that are in containers? All right, let's move on now to energy. Energy perspectives. We're now on chapter 3. And we're basically going to be talking about the ways that energy interacts with food, this first part. And then we'll get on to states of matter and states of matter and transitions between them. But first I want to talk about the forms of energy. And I'm not going to do this for you. I sat down to do this and I thought, no, wait a minute. I'm not doing these guys a favor. I'm actually hurting them by creating the table. If I were a student and I were studying, I would create a table with the information that I'm going to give you. And I was about to do it and present the stuff like that. And I thought, no, I need to give you the opportunity to do this. We're going to be talking about several different types of energy and cooking. And for each one of these, I'm going to define them. I'm going to give you examples. And then I'm going to talk about the pros and the cons. Does that sound like a table to you with columns? I think that you're putting these different types of cooking together after class, because you're going to be a lot you're going to be writing down. When you reorganize your notes, that's how you study. And you start learning the relationships between conduction, convection, induction, radiation. You start learning the connections between those, how they differ, how they're alike. That's called learning. And now you've really got something you can hold on to. So I recommend a table with columns like that. And by the way, take the same studying technique to your other courses. This is how I got through anatomy. The only way I got through anatomy and physiology was tables that I created, forcing me to reorganize my notes. So when we talk about mechanical energy, can I just do the big E for energy, you guys? Is that okay?
That's fine.
All right, nutrition science, we just draw big E. All right, so mechanical energy. And we all know what that means. That means work, right? That means actual mechanical work. And in cooking, that would be things like creaming, beating, mixing, pureeing, all those wonderful things that all those special blenders you guys have, whatever those things are called. All right? And this gives a modest amount, a small amount of heat energy. Can we just do this for heat energy? Is that okay? Is everybody okay with that? All right. So it gives a small amount. So clearly, though, we're not beating to destroy microbes. Why do we cook food, by the way? I didn't even bring that up. Why do we cook it? Yes, sir.
Because their jaws are too small to chew raw food. Because of the way our brains are too big.
Huh. That's interesting. I chew raw food all the time. No, but I hear what you're saying. You're absolutely right. From a certain, there's a certain caveat to that. Yeah.
Oh, I will like one to sanitize it, and then two, like I said, get like tips to get like more calories into your body to like foster like development and stuff. Or say if you're eating bamboo all day, spend all day.
Okay. Yes, sir.
To chemically alter food for easier to facilitate the absorption of nutrients.
Okay. All right, sir.
Denature protein.
No denaturation occurs in chewing.
Oh, I'm
That's
sorry,
in the
I
acidic part, but you do certainly break down from the quaternary structure to the tertiary structure, but not denaturation yet. Yeah.
Also taste.
Taste. Thank you. Well, that's good. How do you know, we're all going science here. What about the taste? Excellent. What was someone else going to say something? Yeah.
To improve the digestion.
Oh, digestibility. Okay. All right. These are all great things. As you know, we're omnivores, meaning we can eat plants and animals. And supposedly fire, the discovery of fire is one of the reasons that we did start developing more mental capacity. And it's because we didn't have to spend all of our time eating. Because by cooking the food, we made it easier to chew. We made it easier to digest. We made those nutrients more available in some respects. Now, we now know there are some nutrients we destroy with cooking, some of our water solubles, but certainly the iron in spinach is not available till you cook the sucker for 10 minutes. So cooking is one of the things that changed and allowed us to develop more. Exactly right, thank you. And then now, there's a certain taste, there's a palatability, absolutely. So all of you are absolutely correct, and coming together, that creates the wonderful definition of why fire and cooking really helped us develop our mental capacity. So clearly, beating, creaming, this wasn't really cooking, was it? But it does create a small amount of heat, just enough to have a very little, let's just say little antimicrobial activity. So it does have some. For example, what are some things that we beat raw and you leave raw? Yeah.
Egg whites, they're marinated. Egg whites, you beat egg whites, you beat it and then you make meringue out of it.
Meringue.
You have to cook it.
He said you cook meringue at about 200 degrees.
Oh, never mind.
No, but you're right. He's right. He's right on 1 degree. He said egg whites. What about the whole egg? Think of a recipe where we use a raw egg and we don't cook it. Mayonnaise. But there's microbial. Well, we puree and beat that stuff to crud. If you've ever made your whole own mayonnaise, you're adding the salmonella, or the bacteria in egg, is killed with a very low heat, exposure to very low heat. That's why you only have to cook your egg for like 30 seconds, and you've destroyed any of the microbes there. So what about something else? One of my favorite things. Anybody like Caesar dressing?
Yeah.
Mm-hmm.
Caesar salad dressing. You just whisk a raw egg. But the whisking is enough. And what do we add to Caesar dressing that has some antimicrobial activity?
Lemon.
The acid. Exactly right, the acid. Like, I love raw oysters, but I kill them with lemon juice. You know what I'm saying? And so when people say, oh, the microbes, well, yeah, there might be some, but I'm adding a slight antimicrobial activity. And so the mechanical energy is small, but it's an important one. It's an important one for some of our raw egg capacity. Let's go on to, though, one of the biggies. I'm going to do this from over here, so I use all three boards. Radiant energy. You know what I'm going to start having TAs do? When I'm through with the board and I'm clear on another one, have your school erase it. I spend more time erasing boards. All right. Okay, so radiant energy. So radiant energy is a direct method of transmitting, it's direct method of transmitting heat energy. And it does this, and we would consider this ionizing, meaning it's creating ions. It does this by irradiating and this usually requires special energy, special equipment that you don't have in your apartments or we have in our kitchens. And what it does is it creates irradiating food, creating ions. And these ions then react with water and bind it. Remember, if we bind water, we're decreasing microbial activity. So these ions being freed from the food, these ions then go on to react with water. And one of the examples that is created is hydrogen peroxide in your food, which has antimicrobial activity. So irradiation then can cause food to last longer. They can be stored at room temperature for long periods of time. So that's an advantage, isn't it? Stored at room temperature for long periods of time. And they're stable. So this is irradiated food, okay? And then there is another type of radiating that you can do at home that's called broiling. That is the direct transfer of heat to food. Okay, there's a whole thing in your book about how this creates gamma and beta rays, and then high energy and high speed. The electrons or the positron is emitted in the radioactive decay, blah, 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 blah. You know, you don't really need to know that. You can read it, it's interesting, but I don't necessarily think that that is really important that you know, unless you're going to be developing cookware. No, I'm serious. If you're developing cookware, you absolutely need to know that stuff, because you need to know how the metal in the pan is going to be reacting with the gamma and the beta rays and just the radioactive material. But I don't really care if you know that for this course, okay? So am I disappointing anyone on that one?
No, you're not.
Those of you who are heavy-duty physics majors, go ahead and learn it. It's interesting, but I'm not going to be quizzing you or testing you on it, okay? All right. He's just cute as a button, isn't he? All right. Here's the thing about broiling. You've all broiled things before. How many of you have burned things because you were broiling and you forgot about it? Yeah, exactly. For this to occur, for this to happen in your home, for you to be able to do this, it requires a constant energy source. So the advantage is it's fast, but it requires a constant energy source. In other words, that heat has to be radiating constantly for it to work. In some ovens that reach a certain temperature and then start cycling, you know what I mean? They get to a certain temperature, they go off for a while, then they come back on. You know what I'm talking about? You can even hear it. Those ovens do not broil properly because they keep shutting down and coming back on. That's why some of you are burning things, because you're expecting it to take them a certain amount of time. It doesn't. You've checked, so you leave. And while you're gone, it comes back on and burns your toast. Also, that's why some ovens recommend that when you broil, you leave the door open. You leave the door slightly open, just a little bitty bit. And the oven will then stay on the whole time. It won't cycle. Yes?
I'm still a little confused about the difference between the broiling function of an oven and the baking function.
Okay, well, baking requires some conduction. Broiling doesn't. It is a direct transfer of heat to the thing. It's irradiation. Okay, we'll get to conduction in just a minute. All right? Oh, it's time to go. All right. Thank you, guys. See you Friday. Don't forget, what's on Friday? They keep that question.